forgot to record. Okay, so in 1900, though there were no sophisticated algorithms like machine learning and deep learning, they had um, statistical models or algorithms like SLR, MLR, which goes way back into the time. But when you are doing SLR or MLR, is mostly MLR, when you have a lot of features for MLR, like 10 features, 15 features. So with the limited computation power they had, it was difficult to make a model with such high features. Okay, so what they wanted was one way of feature reduction. So feature reduction such that your information should be intact, but the number of features should also be reduced. Okay. So that was a motivation that um, because it was almost impossible to handle such data due to the lack of computers. So what did is they try to optimize the number of features. So so what if we can have 2 or 3 very important features instead of having 10 features? So the feature reduction was very important, and so they developed model for feature reduction, and that's called principal component analysis. Nowadays, we do not use it for the feature reduction because we have computational power, but we still use it. So let me just tell you why we still use it. Let's say I have multiple features x1, x2, x3, x4, x5, and so on. Okay. Let's say uh, I converted this data such that retaining all information, but I only have 2 features. Then basically I can plot this data. Remember, we can plot the data only in up to 3 dimensions. We cannot plot anything beyond the 3 dimensions. So if I convert this multi-dimensional data into 2 dimensional data, I can basically plot it to visualize um, what kind of relationship the data have, what kind of patterns, features this data. So PCA help us to do that, and that's why we majorly use PCA. But the idea or concept of PCA started from the need of feature reduction. Any doubt till this point? This is just the
No.
history. Yeah, sorry. You were saying something?
No.
So this is just the background or the motivation behind it. So, so what PCA does is, the PCA, the goal of PCA, the goal is to extract best features. Best features. So let us see what we exactly mean by best features first. Let me just show you a data. Let's say this is my data. I have data of 4 students. their name, class, marks. So tell me, out of this, which you think is the most important feature and which one is least important? So which is more most important and
Marks.
is most or least?
Most.
Okay.
Class is least.
Okay.
Class or age, whatever. One is important.
Okay. You also think age is least important. Okay. Any other think any?
Name also is important, most important.
Okay. Okay. So if I have to choose one most important, one least important, which one you guys will choose?
Marks most and class least. I think name, age, marks are maybe most important.
Most. Okay. But if I, okay, fine. So what you think is marks, age, and all those things are. So all of you agree that class is the least important?
Yeah,
Okay. Why you thought class is the least important?
it's same. They all belong to the same class.
Exactly. So firstly, all uh, all students belong to the same class. So it is not giving me any extra information. What I mean is, all property is same. So, uh, so all properties. So for all of the students, this property is same. Then I can add so many parameters like this, right? For example, if this student is human or not. Okay, for everyone it will be yes. Now, is this feature important?
No,
No, right? Because like this, I can create then thousand features. Does that the person has one nose or not? Any stupid thing I can make up and I can create a class. I can create a feature out of it. But uh, that won't add to my knowledge or information about the students. Whereas look at the marks. Okay, it tells you crucial information such that maybe this student is more uh, active or more intelligent or maybe more involved in the process rather than this person who is getting lower marks. So any some kind of uh, um, observation I can make from the data if I look into the marks column, but I can't make uh, any observation about the students looking at the class column because all of them are from the same class. Age, maybe I can say, okay, this person 1 year elder, so maybe that could have like something we can make out if we have a large data with age and other things. So basically, when we are choosing an important a feature which will help us to distinguish or get more information of the data are the important features. So basically the important feature, so the important feature will have more variance and least important feature will have least variance. So, so the important feature will have more variance and least important feature will have least variance. Okay. So, any doubt till here?
No.
Okay. So, so for the feature reduction, let us see what exactly PCA did. So, let's say I have two features, x1 and x2. Let's say this is the data. Okay. Now, so there are so there are two ways to find the uh, so basically what they did is they started to look in the direction where we have the maximum variance. Think about it, like if I basically their motto was, would there be a single feature which will have information of both x1 and x2? Okay, so they started with an idea. So in which direction or in what feature I can uh, make or I can have such that it will condense all the information that x1 and x2 has. So they start what they started to look is which is the direction in which there is the maximum variance. So think about this diagonal line. Okay, the variance here is the lowest point and highest point coordinates. So basically the distance between those two, or like the difference between the data, that so I can think in this direction, and there is this direction in which there is a variance, right? So these directions and these directions, there are two directions in which they thought. Then they thought, okay, which direction has the maximum variance? So what do you think? Which direction has the maximum variance is difference? Yeah,
Both look very similar.
this is okay. Let me. The green line or the blue blue line? Which one has the more variance?
The green line or the blue line?
Mm-hmm.
Blue line.
Right. So the blue line has more variance. How? What I mean by variance is, so 1, 2, 3. Okay. So the difference between the minimum and maximum point is 2. But let's say 1, 2, and 100, then the difference between minimum and maximum is 99. So this data has more variance than this. Correct?
Yep.
Similarly, when I consider this point, maybe this point on the line and this point on the line, so the it has more variance than this point on the line,
Yes.
this point on the line, and this point. Okay.
Yep.
So what they thought is, let instead of thinking in terms of x1 and x2, let me create the features such that what I should do is I should look in the direction which has maximum variance. So if I consider that, then I can create the features which condense the information of x1 and x2 rightly. Okay. So then they found that the diagonal direction is the direction that has maximum variance. So again, they started to think that in which direction we have maximum variation, and they realized maximum variation is in diagonal direction. So in PCA, from x1 and x2, what we will do is we will create two more features in such a way that it is in the it is in the maximum uh, two features such that one direction data varies too much and other too low. For example, so what I mean is from x1 and x2, we will create two features. Let's call them z1 and z2, such that z1 will be the feature with maximum uh, variance, and then z2 will be another feature with low variance. So in this case, the diagonal blue line is your z1, and this green is your z2. So earlier, this x1 and x2 consisted information. So x1 consisted 50%, x2 consisted 50%. Now in z1 and z2, z1 will have 90% of the information and z2 will have only 5% of the information. So total information will be 100%. Okay. So z1 and z2, if I add, total you will get 100% information. But even if I remove z2, uh, I can retain 95% of the information. By, but I can lose 50% of the data. So I can reduce the memory by 50% with compensation of loss of 5%. Now we can throw out z2, which wasn't possible earlier. So earlier we couldn't throw out x2. Okay, but now we can throw out z2. It will reduce the data little, but that much, if we compromise on 5%, we can reduce the dimensionality by 50%. Is this clear till now? Is there any confusion? So remember, PCA won't tell us x1 is more important or x2 is more important, but they will create new features such that one is extremely rich in information and another is low in information. How it will create those features, we will look into it. But as of now, just remember it that PCA won't tell you which feature among x1 and x2 is important. What it will do is, given x1 and x2, it will create z1 and z2 such that z1 is almost 90%, 95% information, and z2 is 5% information. Okay, so that way I can keep z1 and throw out z2. So it allows me to throw out. So let me give you an example of what I mean by. So let's say you have this data x1 and x2. So 1, 2, 3, 4, 5, 6, 8, 9, 10. Okay. And then I have Z1 and Z2. Okay. So Z1 is, let's say, 3, 7, 11, 15, and this is -1, -1. Okay. Now you can see that Z2, majority of the information is in Z1. Z2 is almost not important data, not important feature. Okay. So that way you can throw out Z2 and retain majority of the information using Z1. Is it clear till now the what we are doing, what we will try to do?
Yes.
Okay. So let me just summarize what PCA will do, what PCA does. First, it takes data. Okay. Then for that data, it will find directions with maximum variation. Let's call that Z1. Okay. Then third thing, then Z2 will be such a way that angle between Z1 and Z2 is always 90 degree. So whichever is the so if this is the Z1, Z2 will always be perpendicular to it. So that is, so once we find Z1, whatever is the perpendicular, that will be Z2. Okay. So then, so what it does is it takes the data, it find the direction with maximum variation, that is taken as Z1, and then Z2 will be such that it will create a 90-degree angle with the current direction. So and also x1, x2 and z1, z2 are interconvertible. So, so from x1, x2 you can get z1, z2, and from z1, z2 you can get x1, x2. So let me just give you an example how we can do that. So we have 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is the data, and the z1 was 3, 7, 11, 15. All this is mine. This was our data earlier. So let's say x1 is equals to z1 minus z2 divided by 2. Okay. And then x2 is equals to z1, sorry, plus and then minus divided by 2. If I calculate x1, for the first scenario. So 3 minus 1 divided by 2, which is 1. And then x2 will be equal to 3 minus of minus 1 divided by 2 is equals to 4 divided by 2, which is 2. Okay? This way I can calculate all the values of x1 and x2. Similarly, if x1 and x2 is given, I can just calculate. So z1 is equals to x1 plus x2 and z2 is equals to x1 minus x2. So I'm just showing this as one example, but there are different ways to calculate so there is one way in which we should calculate the direction of the maximum variance, but I'm just showing how basically we can form new variables or new uh, so yeah, so from x1 and x2 how you can get z1 and z2 such that you will have the maximum information retain. So any doubt till this point? So basically what we are doing is, this was our data earlier. From here, we are going to the data like this. This was x1, x2. From here, we are going to z1 and z2 such that data is like this. The constant z2, which was so constant z2, so that I can, even if I throw z2, I won't lose much of the information because majority of the information is in z. So here, in this case, first case, both x1 and x2 are changing too much. But in this case, z1 is changing and z2 is almost constant. So z1 has almost 95% data and z2 has just about 5% data. So if I throw z2, I can save 50% of the space just by compromising on that 5%. But now we don't use the feature reduction to save memory, but what we can do is plot the data. If I have 3 features, 4 features, if I reduce it to 2 features, I can plot that data and visualize. So for more than 3 features, we can't plot the data. So what PCA will do is it will give uh, features. So let's say if I have data x1, x2, x3, x4. Okay. From this, it will give us data z1, z2, z3, z4, such that z1 will be 70% of the data, z2 will be 25% of the data, z3 will be 3%, z4 will be 2%, let's say. So what I can do is I can retain only these two and throw these two out. So I will have 90% of the data with me. 5% data will be lost, but in order, but with that, even though lost the 5% data, but I have 95% data, and now this data I can plot. and visualize, which was not earlier possible with this. Is this clear? You know if this is clear.
Yeah.
Are there any questions, any part which is not clear? Because if this is clear only, then the next part would be straightforward. Take 2 minutes and let's just uh, go through what we discussed and let me know if there are any questions. So no question?
It's fine. I think.
Okay. Okay. Now only thing that is left to discuss is how exactly we calculate the features Z1 and Z2 such that we get information like this. So majority will be in the Z1, then little less will be in the Z2. Z3, Z4 will almost have very less data. Okay. So let us see how we can calculate or find such features. So for this, we will need to know two concepts. First is matrix multiplication, and second is eigenvalue and eigenvector. Just a second. Yeah, sorry. So one thing we will need to know is matrix multiplication, and another thing we will need to know is eigenvalues, eigenvectors. So let us start with the matrix multiplication. So firstly, let's say I have this matrix A. We call this matrix A. So it has 1, 2, 3, 4, 5, 6, and this is 2 cross 3 matrix. Then I have another matrix, let's say. This, let me call this B. So 1, 5, 7, 8. This is 3 cross 2 matrix. That means it has 3 rows, 2 columns. This matrix has 2 rows, 3 columns. Now, can I multiply A and B?
Yes.
So, why we can multiply it? There is a rule for the matrix
Yeah,
multiplication.
matrix rule, like multiplication rule, right?
Yes. So if the number of columns in A is equals to number of rows in B, then only we can multiply the matrix. So first is 2 cross 3, 3 cross 2. If you write it side by side, if the inner values are same, then only you can write the make the matrix, do the matrix. So for that, if you have P cross Q, then you can multiply it only if your B matrix has Q cross. It can be anything. Let me call it R. Then your after A cross B, your um, sorry, A dot B, your after the multiplication, whatever your resultant matrix is, that will have dimensions P cross R. So here the resultant dimension will be 2 cross 2. Clear? So if I have A P cross Q and B Q cross N, then the final dimension after multiplication will be P cross N. So let us see how to now do the multiplication. Just take 1, 2, 3, 0, 1, 0, 1, then 2, 0, 0, 0, 1. Let's take this. This is 3 cross, sorry, 2 cross 3, and this is 3 cross 2. As this is equals to this, so we can do the multiplication. In order to multiply, so take the row and take the column, and then so 1, 2, 3, and then take the column 2, 0, 0, then this multiplied with this with this, and this with this. So then when once you multiply, so it is like uh, this if you write side by side. So 2, 0, 0, 1, 2, 3, and take the multiplication of all of them and add. So the resultant will be 2, 5, 2, 1. Oh, the 2 crossed. Pravadi, have you studied matrix multiplication before?
No. I guess I have in that video.
Okay. So is this clear, or should I write
No,
again?
it's clear.
I mean, I can explain one more time if you have any doubt. Is this it's clear?
Yes.
Okay. Then once this matrix multiplication is done, let me just quickly go through the eigenvalues. So let's say if I have this matrix 1, 2, 2, 1, and if I multiply it by another matrix 1, 2, then the resultant matrix will be 1 into 1, so 1 plus 2 into 2, which is 4. 2 into 1, so 2 plus 2 into 4, sorry, 1, 2. Yeah, sorry, here also 2. So the resultant matrix will be 5, 4. 1 into 2. That's why 2. So let us understand what exactly happened when we multiplied it by another matrix. Let's say this is my x2, this is my x1. So earlier, this was my point 1, comma 2, right? 1, comma 2. So this was my point. When I multiplied by another matrix 1, comma 4, what happened to it is it became 5, comma 4. Okay. So when I multiplied with 1, comma 2, so this is 1, comma 2. This was my earlier this thing. When we multiplied by 1, comma 2, so when we multiplied by one vector, it shifted the point to 5, comma 4. Right. Now, after multiplying a matrix with a matrix, what it did, it basically, so from initial point 1, comma 2, it went to 5, comma 4. So so the matrix multiplication can rotate, and also it changes the magnitude. So earlier it was this, so it rotated the matrix, okay, and it also multiplied the matrix. So, so rotated, so this is our one matrix, and then it multiplied it maybe 3 times to get to the point 5, comma 4. I mean, just taking a hypothetical scene that it is multiplied 3 times, but whatever it is multiplied with. So what it did is it rotated the vector and also multiplied the vector. So it changed the direction as well as the magnitude. Okay. So this is what normal vectors do after the multiplication. They change the direction of the vector and then they change the magnitude of the vector. Now eigenvectors are special. So basically what eigenvectors is true. So eigenvectors will change the magnitude after multiplying it. It will change the magnitude, but it will not change the direction. So let us see. So it can do anything with magnitude, but it won't change directions. So there are two things that can happen with the magnitude. It can either magnify or increase, and sometimes it won't magnify, or it can reduce the magnitude. Okay, so only those two things can happen with the magnitude, but direction won't change at all. Okay, so let us see one example. Let's say 1, 2, 2, 1, let me multiply it by 1 minus 1. Then what I got? Minus 1, 1. So if I take the minus 1 out, 1 minus 1. So this is my eigenvalue, and this is eigenvector. A vector such that, like, if I multiply it to any other vector, it won't, not any other, but eigenvector of that particular vector. If I multiply the eigenvector, it won't change the direction, but it can change the magnitude in such a way that it can either increase the magnitude or reduce the magnitude. Okay? So eigenvector won't change the direction, it will change the magnitude. Sometimes it will make the magnitude too high, sometimes it will make the magnitude too low. So the direction is where so direction where the magnitude is maximum, those are the direction where you have the maximum data. So if eigenvalue or magnitude is high data, and in low is low, then low data. So let us see an example. Just like we have calculated this before. If I multiply it by 1 minus 1, the vector I got is minus 1 of 1 minus 1. Right? Now if I multiply by another eigenvector, which is 1 comma 1. So if I multiply, I will get 1 into 1 1 plus 2 into 1 2. So 2 into 1 2 plus 1 into 1 1. So 3 3. So if I take 3 out, 1 comma 1, this is retained. Now we have two, so these are the eigenvectors. These are the eigenvectors. Eigenvalues, and these are vectors are the eigenvectors. So now I got two eigenvalues, minus 1 and 3. So 3 will have maximum data, minus 1 will have least or minimum data. Basically, this will be the direction in which there will be maximum change. This will be the direction where there will be least change. So any doubt till now?
Fine.
Okay. So if you think of basically these are the two vectors. So was, let's say this is 1 1 2 1. So yeah, so these are the two. Then by the law of fixed addition, you will get a parallelogram, right? Now this is the direction of maximum change. Let me call it A, and this is the direction of minimum change. Let me call it B. So in our example, A is equals to 1 comma 1 and B is equals to 1 minus. This has eigenvalue 3. This has eigenvalue. Okay. So this one will have maximum variation and then maximum data. This has minimum variation and so data will also be minimum. Okay. So from x1, x2 up to xn, from these features, what we are doing is we are going towards the features z1, z2, and so on up to zn, such that z1 is more important, z2 is second most important, and so on up to zn. So you will go on, the importance will go on reducing. And then once you have the uh, eigenvector, so take the transpose. How you take the transpose? Okay. A is equals to 1, 2, 1, 2, 3, 4, 5, 6, and then A transpose will be equal to 1, 4, 2, 5, 3, 6. So X transpose P cross M into X, which is M cross P, let's say. So then you will get P cross P matrix, right? Now, so in order to calculate the, so basically when you will do X, and multiply X transpose, take the X transpose multiplied by your vector, then you will get multiplied by eigenvectors, you will get eigenvalue into that vector. This is eigenvalue. Once you get eigenvalues for that, arrange it in such a way that it is decreasing order of the eigenvalues. So lambda 1 will be greater than lambda 2, it will be greater than 3, and so on to lambda n. And then your z1 will be equal to x into v1. Then your z2 will be equal to x to v2, so on. This is how you will get the features. So let me just summarize it. So first, take the data, second, find eigenvalue and vectors. Okay. Third, arrange in descending order. of eigenvalue and then for calculate features by z is equals to x into v. Tell me if you have any doubt in any step.
Uh, if we calculate the features
Mm-hmm.
z is x into v,
Ah,
then why are we arranging this in descending order?
okay. So if we only when you will order in the descending order, you will get to know which is important feature and which is not important. So you let's say you have x1, x2, x3 up to xn features. Now each time you will multiply by uh, your eigenvector. Then what you will get is eigenvalue into that vector. Okay. Now what we are saying is if your eigenvalue is high, that has maximum data. If your eigenvalue is low, it has minimum data. And we want features such that z1 has maximum data, z2 has a little less data than or less the data than z1, then z3 has less data than z2, and so on. So your how much data z1 will have is directly proportional to what is your eigenvector, eigenvalue. So that's why we arrange it in the descending order, so that corresponding z1 will have highest value, highest data, corresponding z2 will have second highest data, and so on.
Okay.
Clear?
Yes.
Okay. So entire theory is clear, right?
Yes.
And no doubt in the theory.
No.
Mahesh and Prabhari,
Fine, fine,
sorry, I couldn't hear you.
Yes, it's fine.
Okay,
fine, fine.
okay, okay. Then I wanted to do uh, coding part for this, but can we uh, can we meet around 1 o'clock? Like let's have lunch and everything, and then we can meet at 1 o'clock, and then we can continue the coding part as well as I was thinking I will take SVM today. Is that okay?
So, for approximately for how, up to what time it will be there?
So if we meet at 1,
Mm-hmm.
then we can continue till 2:30.
Yes.
Is that okay?
Oh,
Yeah.
okay.
Then we can cover the coding part for this as well as the theory part for SVM.
Okay.
Okay.
Okay, then let's see you guys at 1 o'clock.
Yeah.
Okay.
Okay, okay.
Yeah.
Bye bye.
Bye bye.